Hello, hello. Testing, 1, 2. All right, good morning, everyone. Good to see you back. Let me mention some more about our first project, what you need to do. So, in this project, I want you to find your own title. Okay. So inside this project, right, for the first part, I want you to do survey on the title. For example, let me write an example. So for example, last lecture we stopped at the what do you call that theorem again? The monotonic sequence theorem. Okay. For example, we didn't do this in class, so maybe you might want to know why this is true and then how to establish this theorem. So first, what I want you to do is you go and survey maybe on the history or the background. Okay. Maybe you need to find the first paper that mentioned this theorem or proved this theorem or anything. Okay. So first part, you need to talk about history, background. Second part, you need to write about the theory, the setup, all the definition required and proof. Okay. And then third, I want you to show examples in mathematics. Okay. So for example, if you prove the monotonic sequence theorem, then you need to give a few examples to show us how to use this theorem. So examples in mathematics questions. Okay. And then with your references. Okay. I think a good place to start is Wikipedia. So you can look through Wikipedia and then follow the references in the Wikipedia and then follow the references inside the Wikipedia. Okay. I mean references that referenced by Wikipedia. Okay. And then all the reference therein. So this project, I guess at least 1.5 pages. Okay. You can go up to 3 pages at most. Okay, no need to go more. So because What the purpose of this project is for you to develop the skill to survey a new knowledge that you wanted to know, but it is found. It's already been solved. Okay, and then see if you can understand what people wrote, understand what people proved. Yeah. Okay, but I encourage you to come and keep talking to me whether this topic is suitable or not. All right, because if you pick a topic that's too short to write, then there's no much point to do. Okay, so I mean, when you get along with lectures, right, we will we will let out some of the proof for important result. Then those topic will become a topics that you can write. Okay, so we don't cover in the class, so you go and do your own research and then you learn better. Okay, so the purpose of the first project is this. So first project, I think deal in 2 months time. Okay, so you still got time. And if you also can come up with your topics when you read through the textbook and then you see, hey, this textbook doesn't explain well, and then I go and look for more references, and then this will become your project. Okay, so it's quite free. Yeah. So idea from lecture or your own reading. Okay. So briefly, roughly, I will mark based on a few criteria. So one is language, of course. I found that the language here, the student here is not very good. So language, how to spell? I also forget how to spell already. This is it. Okay. So I mean, not about spelling, but at least you need to write something that makes sense. Not about grammar or vocab, but you need to write something that makes sense to English reader. Okay. Maybe you like direct translate from English, from Chinese or other languages. So make sure you write something that makes sense to the English reader. So how you improve your English? So if you read more English paper or English stuff, then you will improve more. Okay. Uh, two is the completeness. Okay. So by completeness, meaning I need to be able to follow the flow. So you have some background, some history, why we want to consider this theory, and then we want to set up the machinery to prove this, and then how to prove it, and then how to use this result. Okay, so the completeness is based on these three, basically. And then let me put marking criteria here. What else? Third is the difficulty. Okay, so if you can explain some very hard result, then you can get more marks. But if you try to pick very hard topics but you cannot explain it well, then this is a give and take. Okay, so so this total is just 10%, but I will list out the further breakout. The moment I think about here, maybe 2%, maybe 4%. So language is for you to explain well what you want to talk about. Completeness is whether what you talk about makes sense or not. Is it uh, is it understandable? Okay, by other people. Okay, so far it's like this. Then I will put into black and white soon. Okay, and then hopefully assignment 1 will be out this weekend. Hopefully. Okay. So far, you have any question on project? You can start thinking about project title already, and try to talk to me more whether it is suitable or not, and also talk to me on how you're gonna proceed with this thing. Okay, does it make sense? Okay, so this is a brief guideline. So yeah, depend on how you uh, do. Okay, then we can make this project better. So find any question? And remember that I asked one question in the start of the class last lecture. Why do you choose mathematics? I don't have an answer from you. So I give you 1 semester to think. I will ask you back in the last day. Okay. So maybe this is one of the question in your presentation. Okay, I give you 1 semester to think. All right. Yeah. Any question? Any also other question from last lecture? Any question from last lecture? If there is no, that means two things. Either it's good, you understand everything, or it is very dangerous. Maybe you don't understand something. Okay. So try, if you have question, make sure you ask me. Okay. Don't keep it to yourself because it will grow like a snowball. Okay. So let's recall what we did last time. Okay. So we characterize a few sequences. Right? We characterize a few sequences. Okay. Sequences we can label by a set of AN and indexed by natural numbers, right? So they are discrete. So we can talk about increasing sequences, right? If it is increasing, that means the next term is always greater than the previous term, okay, for all n. And it is non-decreasing if the next term is always greater or greater or equal to the previous term. Okay. So in this case, you can do a symmetry on this inequality where you can define decreasing and non-increasing. So decreasing if for every next term it is strictly less than the previous term. And non-increasing if the next term is always less than or equal to the previous term. Okay. All right. So you remember the picture I drew last time? So either it's strictly going up or it's going up like a staircase, not increasing. So is it true that every increasing sequence is a non-decreasing sequence? Yes or no? Yes. Okay. So because it satisfies an less than an plus 1. Okay. All right. Do I need more now? Okay, maybe we don't need more. So let's start with this example as I promised last time. So we want to show that the sequence n over n plus 2 is increasing. Okay, maybe we need to address whether this sequence is bounded or not on the second part. Okay, so to show that the sequence is increasing, what do you need to show? Any idea? N smaller than n plus 1. Okay, so in this case, okay, we need to show that the sequence, maybe I name it an, is increasing. We need to show that an is less than n plus 1. Okay. Okay. So how on earth you going to show this? Right. So you can that is we can show that n plus 1 minus an is greater than 0. Okay. So you can take the difference and then see whether it's greater than 0 or less than 0. Right. So let's do it. So what is an cubed? What is an plus 1 minus an in this case? What do you get? So I sub n plus 1 into n, where I get n plus 1 over n plus 1 plus 2 minus n plus 1 over, n over n plus 2. Okay? So what do you get for this? I'll just skip this step. It's okay. So you can compute yourself, and then what we get is 2 over n plus 3 times. So you make the denominator same, and then you add up the numerator. So what's this number here? N lies in where? Where does n lies? Natural number. Okay, so natural number is always positive. Okay, so you add a positive number, you still get a positive number. You multiply two positive number, you still get positive number. So positive number divided by a positive number, you still get positive number. Okay, so this number is greater than 0. Okay, so to be precise, right? So make sure you can write addition, multiplication, division of positive number is positive. The product, the sum, and the product and the sum of positive number is positive number. Okay, you can quote this result. So to be precise, right, you can quote the product. Have you guys proved this result before? I think sum of positive number is positive is proven in discrete math, right? Sum for sum, is it? Or products. Have you guys seen this result before? The product and sum of positive number is a positive number. I remember I proved some of this in the discrete math. Yeah, it's not hard to prove, but you need to prove from the axiom of numbers. Okay, so this is greater than 0 for all n greater than or equal to 1. So this is what we want. Okay, so this sequence is positive. This sequence is increasing. Okay, so by definition, okay, not that I already named my an here, so I'm not arbitrary an. So I already named the sequence as an. Okay. Okay. Any question on this part? So the increasing or decreasing, you just take the difference and then see you can deduce anything from that sequence, the difference or not, for all n. Okay. Make sure that it works for all n so that it doesn't alternate up, down, up, down, up, down. Okay. So it must be true for all n. Okay. So in mathematics, right, this quantifier is very important. Yeah. Is it for all or for some? Okay. So for all, you need to check for all. Okay. Maybe you will ask, why not if check for all and why not we use mathematical induction? Right. If you want to check for all and supposedly you need to use mathematical induction, right? You check the base case, check the assume the hypothesis, what's that? inductive hypothesis, and then you do inductive step, right? So because this argument actually work for arbitrary n, so this work. Otherwise, if it's not clear, then you need to do mathematical induction. Okay, so be careful when you show something if for infinite. Okay. Okay, so is this sequence bounded? Okay. Remember what's the definition of bounded? What's the definition of bounded? You can recall. A sequence AN is bounded if it is bounded above and below. All right. Yeah. So in mathematics, also very important. Whether I put an N here, I put an O here, make a very big difference. Okay. If I put an N here, that means you need to check two things. Okay, both true, only this is true. Okay, if I put O here, then either one of them is true. That's fine. Okay. So N and O very important. For example, here, this is less than or equal to. It's not less than N equal to. Okay, so it's very important here. N or very important. Okay, so note that I have some glitch here. I tell you that bounded if it is bounded above and below. But I didn't tell you what is bounded above and below yet. Okay, so you need to go back the definition to bounded above and below again. Okay, so let's dig back the definition. What is bounded below? Okay, so a sequence AN is bounded above if there exists an M. Okay, this M we might as well we can pick it from N or R. Maybe I pick from N. There is an M in N such that AN is less than equal to M for all N greater than equal to 1. Okay. So it must be true for all N. Okay. It can't be that maybe the first term is greater than M. So it's not possible because you want to bound everything. Okay. If you can bound everything else by an M, but you cannot bound the A1, right? What can you do? Okay, let me draw it so you can have something to. Okay. So let's say I have a sequence that I can bound with M, but the first sequence is up here. Okay. Can you bound the whole sequence? Make it bigger than A1. How do you make it? And do it precisely, I mean, here. You can, okay, let's call this A1. So you just add the difference between A1 and M. Maybe it's greater than 0, so I'm going to put this. So you make your new AM prime here. Okay, so you add the difference. Okay, so far, okay. Okay, okay. There's nothing deep here, by the way. So I mean, yeah, if you don't have big enough number, so you need to add more stuff to make it bigger, such that you cover everything inside your sequence. Okay. Okay. So M is equal to M prime is equal to M plus A1 minus M, which is A1. So actually the first term will bound everything else. Of course, if you are naughty enough, you want to pick A1 plus 1 also can. Yeah, A1 plus 1 also bound everything else. So there's some freedom here to do, but anyway. Okay, so similarly, you can define bounded below using the similar definition. You know how? Oh, what's the definition of bounded below? It's bounded below if there's this a number. Okay, maybe in this case, I need to change to R so that it's easy. So it lies together with A1, so I can pick A1. Otherwise, I need to do trick. So such that AN is greater or equal to M for all N greater or equal. Okay, so usually this definition, right, have some duality. So you just switch the inequality or you just switch the, yeah, there's some duality happening. All right, is it clear? So there's some small m and big M bound your sequences if a sequence is bounded. Okay. Okay. So in this case here, let's look at this. This example. Do you think this sequence is bounded? So you don't think from, don't uh, start from what you have. Okay, what do you have about this information here? This sequence is what we have just shown, increasing. Okay, so you can ask, is it bounded below? Is it bounded above? Okay, increasing. I already draw the picture for you, right? Increasing is like going straight up. Okay, is it bounded below? Bounded below by what? A1. Okay, so first of all, you know that it is increasing, you know that it's bounded below by A1 because our sequence start with the finite point. Okay, A1. We start with A1 and then keep increasing, right? Okay, so in no space. Let me start a new page. Okay, so we know that n over n plus 2 is increasing. Okay. Since A1 is what? Since A1 is, what is A1 in this case? A1 is 1 over 3. Since A1 is the first term, the sequence increasing, the sequence is bounded below by 1 over 3, which is A1. Okay, by 1 over 3. Okay, so how about bounded above? And then what? N going to be and then so what? Take the limit. Sure, if you want to take a limit, just take a limit. So what do you get? 1. Okay. So maybe you want to see whether it converges or not, right? So you see whether it converges or not. So let's take. So you want to check whether it is converging or not. So you can take the limit. Okay. So the trick I told you last time is actually just rewriting this sequence here. Okay, so you can do a trick which is multiplied by 1 over n on both numerator and denominator, which you get 1 over 1 plus 2 over n. You should see that really these two define the same sequence, right? So if you write out the sequence of this guy is also the sequence you get from the original sequence. Okay, it's just rewriting. Okay, but this rewriting here, right, will help to compute the limit. Okay, so really, yeah. So you can see that what property or theorem you can use here, compute this guy. How to compute? What tool did we learn last time? Oh, by the way, I put out the fine tune. I mean, I already adjusted the lecture notes and then I put it on. Have you guys seen it? Okay, yeah. Okay. So afterward when you do revision, you can use that version. And then let me know if you found any mistake. Okay. Yeah. Okay. So come back to here. So how to compute this limit here? You want to go through real function. Sure, you can go through real function. Okay. So let's go through real function then. So to compute this, there's a theorem say if limit x go to infinity 1 over plus 2 over x is then limit of x infinity of 1 over sorry, this is n. Okay, so if you want to go through the real value function, is the theorem that if the limit of the real value function is equal to L, then the limit for the sequence is also equal to L, right? Okay, this is the real value theorem, convergence of real value theorem that tells you. But I'm an algebraic person. I don't like analysis, so I prefer more on algebra properties. Okay, so to use algebraic properties, we need to use the properties of convergent sequence. Okay, so if we regard these terms here as sequence, okay, so for example, 1 is a constant sequence, 1 here is another constant sequence, 2 over here, and here is a convergent sequence. Okay, converge to what? 2 over n. 0. Okay, it's the same as 1 over n, right? Then you multiply by scalar, it still converges. Okay, so if we have a starting point, so let's say we have a starting point, we know that 1 sequence of 1 and okay, this one I list as method 1, I list method 2 here. So we know that 1 and 2 over n converge to 1 and, sorry, let's start from very basic 1 over n. We've shown this in class yesterday. Okay, converge to 1 and 1 over n, sorry, 0, 0 respectively. Okay, so by what? By property of limit of convergent sequence. Okay, we have what? We can bring the limit all the way into the expression. Right. Okay, so where we get 1 over 1 plus 2 times 0, which is 1. So in future, I might not go this detail, but every time I say something, right, you should have this detail, this kind of detail in your mind. Okay. In future, we will speed up. Okay, we won't go into these details. So in future, maybe I say, you can use the real value theorem to prove it. So you should, at your mind, you should exercise this part. Or we can use the property of limit, then you should exercise this part in your mind. Okay, in future. We will go quicker and quicker, but I want to let you see how detailed we can go. Okay. Okay. Sure. So the limit is 1. So that means what? That means, does this imply, so this implies that 1/3 is less than an is less than 1. Okay. So it is bounded below by 1/3. It is bounded above by 1. N over n plus 2 is bounded. Okay, note that you don't see me putting equal sign here. Actually, you need to check. Okay, check that whether you can achieve 1 or not. You know how to check? Check. So you just let an equals to 1 and over n plus 2 is equal to 1, and then you will get that 2 equals 0, which is a contradiction. All right. Any question on this example here? Question? No? Okay, if not, then we will skip the next example. So you can, I will left as a homework. It's showing another sequence which is decreasing. Left as homework. Okay. After that, in the very last end of this our lecture last time, we mentioned about the monotonic monotonic sequence theorem. Okay, so this theorem is quite useful and very important in mathematics. So it's okay we mention more times. So every bounded monotonic sequence is convergent. Okay, so just now we talked about bounded sequence, but we haven't recalled what is a monotonic sequence is yet. Okay, so what is a monotonic sequence? Anyone can recall? Increases or decreases? Huh? Increases or decreases? Oh, actually, there's slight subtlety here. Okay, we have strictly monotonic and monotonic sequence. Okay, so when it is strictly, it is increasing or decreasing. So when it is monotonic, it is non-increasing or non-decreasing. So that means this theorem allows sequence that like going like a staircase. So you can equal sometimes, but you can continue or you can stagnant at some point. We allow that. Okay. So imagine if it's stagnant at some point, what is the limit? So okay. Let you think about it again. So if you have a sequence that you cannot go down because it's keep going up or stagnant. So let's say your sequence get stagnant at some point. So what's the limit? Yeah, that's the stagnant point. Okay, it's the limit. Okay, so this is your So this case is easy, but the not easy one is, let's say it stagnant, move a bit, stagnant, move a bit, move a bit. Okay, so how? Okay, of course, it is not bounded, then it will go forever up. But you know that it is bounded, that means it must converge to somewhere. Correct. Maybe you will think, if it is bounded, why not just reach that limit? Why not just reach this limit? You ever think about it? So let's say we got a limit here, right? Okay, we got a limit here. L. So if you are increasing, okay, why not just reach this point? Why there exists another case, maybe it doesn't reach it, but it's there very close to L. Okay, why not we just reach the L? Do you ever ask this question? I mean, will you ask this question? If it is increasing, okay, it is bounded. Why not it just reach that limit? Did you get my question or not? Yes? Okay. Yeah, so this has something to do with the property of the real numbers. You can infinitely arbitrarily close to a point, but you never reach it. This is something to do with our real number. It's very dense. I mean, yeah, dense. Okay. Anyway, we don't pursue this subject yet. So let's look at this question here. Okay. But any comment? What's the answer question? Oh, I just broadly say the answer is like the property of real numbers. You can make such kind of sequence. But what property? I didn't tell you. Yeah. So I want you to think about it. Go and find it. Okay, maybe it's a project question. Okay. So you can try and find the density of real numbers. Okay, it'll be something like this. Okay. So yeah. I cannot tell you everything in the class, right? We need to cover something in the class. So, but I want to stimulate you that there's something going on. There's some other things are going on. Okay. So yeah. Okay. Yeah. Okay. So this kind of question is a bit pure. So suppose that you know that a sequence is increasing. Okay. Don't know what sequence is it? Any increasing sequence, and all the terms lie between 1/3 and 1. Okay, so in particular, the example just now is satisfying this condition here, right? Okay, so I explain why the sequence has a limit. Okay, so this tell you that you don't need to compute the limit. I tell you why there's a limit. Okay, you don't need to compute, but I can prove to you why it has a limit. I don't know what's the limit, but it has a limit. And what can you say about the value of this limit? Right? Okay, so we learned about this monotonic sequence theorem. Okay, so it says that every bounded monotonic sequence is convergent. Okay, so you want to show something has a limit, converge to a limit. So maybe you can consider this theorem. Okay, if your sequence is bounded monotonic, then it has a limit. Okay, let's see if this condition here satisfies this uh, condition that needed in the theorem. Okay, so you know that an is increasing. Okay, so is it monotonic or not? Monotonic or not? Why? Yeah, because yeah. Okay, good. So let me write down. Yeah, good. So okay, I don't write the sentence down now. Okay, so I just write the key point. So increasing implies monotonic. Oh, sorry, not yet. Increasing imply non-decreasing. So I'm just saving time without writing the long sentence now. I'm trying to how to say keep shorter and shorter. But in your assignment, you need to write the full sentence now. Okay. So increasing implies non-decreasing. Non-decreasing by definition is monotonic. Okay. So it is a monotonic sequence. First of all, you still need to check bounded. Okay. Is this sequence bounded or not? Why? Okay, so follow back to the definition of bounded. So it is bounded below, so there exists an M which is 1/3, bounded below by 1/3, and bounded above by 1. So it is bounded. Okay. Hence, by monotonic sequence theorem, hence by monotonic sequence theorem, AN is convergent. Or in another word, it has a limit. Because in our definition of limit and converge, they are the same. Can recall? No? Can recall? That is AN has a limit. So what can you say about the value of the limit? What can you say about the value of the limit? Again, equals to 1. Equals to 1. Less than or equal to 1. Sure. Okay. Anything else? Bigger than 1. Oh, bigger than 1/3. Okay, okay. Bigger than 1/3. Okay. So why can you deduce this? Why can you deduce this? So claim. So your claim is 1/3 less than lim n infinity an less than equal to 1. So why? Obvious. So why? What else theorem you learn? Squeeze. Okay. What did squeeze say? What did squeeze say? Anyone recall what the squeeze theorem is? If Bn is bounded by An and Cn, and An and Cn are converge to the same limit, then the middle one converge to the same limit. Okay. But in this case here, you don't quite have those things, right? Because one converge to one and then 1/3 converge to 1/3. Okay. But I guess you can modify the proof and then ensure that the middle sequence actually converge to something in the middle. Okay. If you are not happy with my answer, make it a project, then prove it. Yeah. Seriously. I'm talking seriously. Because this is how to say, we can actually write this thing very precise. Okay. But we won't do in the class, so I want you to do it outside the class. Okay, so make it a project. So you can modify the squeeze theorem and then say that if I squeeze by two convergent sequence that converge to different limits, then the middle guy should converge to something between these two limits. Okay, so if you can get this question, yeah, so get this question and then go back and prove it, also can become your project. Okay, but first you need to understand my question first. Then. Okay. So my approach to here is proof by modification of squeeze theorem. Okay. So okay, not that here we don't put equal to 1/3. Do you know why? You know why? Yes, because the next arc A2 is already greater than 1/3. Okay, so you cannot 1/3 is away, like how to say, A2 minus A1 away from the sequence, at least. Okay. So you cannot make arbitrarily close anymore. Okay. Yeah, so can be equal to 1. So in the previous case, what did we found? We found that that sequence actually converge to previous example, converge to what? converge to 1. Okay. So the limit of the AN should be. Okay. So this shows you that the powerful of theorem. Okay. So this theorem can be used for any cases that satisfy this condition here. Okay. So don't say that some pure max is nothing, but you need to know why something is true. Otherwise, doesn't make sense. And how to use it. So that's why I built the project. So you know the theory, and then you have to know how to use it. Okay. Use some examples. Okay. So far, okay. Okay. Let me see. It's 1148. Uh, okay. Maybe we skip this. We skip this. So I left as a homework. You want to do this or can you do as a homework? And okay, left as homework. Okay. So we can go to the next new topic. But if at home you feel that my solution doesn't make sense and then you really don't know how to do it, you can email me and then we can bring it out again in the next lecture. Okay, so we find time doing it again. If you can digest yourself, then that's good. If not, please bring it back to the lecture and then I will explain again. Okay, is it okay? Okay. Okay, I'm not trying to skip any question, but I want you to be more independent. Because I want to say something that's not in the textbook or lecture note. Because for those, you can read it yourself, I think, right? But for some insight, maybe you can't see it. So I will tell you what I see. Does it make sense? Make sense? Okay. Okay. So because also we have limited time, so we have to give and take a bit. But if you're really struggling, you should let me know and then I will adjust. Okay, based on your needs. Okay, before should we take a break? We take a break. Okay, let's take a break until 12 o'clock and then we will start series. Hello. And also one advice for you, right? Okay, when you do the question, don't think wildly. Okay, start from what you have learned. Okay, so keep all the theorems, the properties in your toolbox first. Okay, write down in a paper if you want. Do a summary. When you do a question, take it out. Okay, compare which one I can use. Okay, and then start from there. Because now first year is very easy because everything we build up one by one. So you only have these two, you should use these tools. Okay, and then slowly we will build up, build up. Don't do the question like from nowhere. Okay, so we have this theorem, we have this property, so you should at least know all these and then use this. Start from this. This is your starting point. Okay, I mean you have a starting point. Okay.
So for the project, we need to choose some topic in class.
Or anything.
Anything else? About calculus too. Just
Yeah.
Okay. Underwrite a report or something.
Oh, okay. I will write it in black and white later, but the idea is you pick a paper. Pick a paper or pick a theorem or pick any topic. Write about the history or background if it is proven, and then set up. You need to introduce enough definitions and then prove this theorem or theory, and then come up with examples how to use this theorem, and then list down your references. So at least 1.4, 1.5 pages, up to 3 pages at most. No need to write long stuff. I just want you to understand one theory and then be able to explain that theory or write it in your own words. Don't copy plagiarism. So I will mention again later. So, and then the marking criteria is like 4% for your language, 4% for your completeness, and then how difficult is your thing. So if it's difficult, then maybe we'll get more marks. But if you write difficult stuff, then you maybe don't write well, then you will take marks from completeness. So yeah.
So project need 10%.
10%.
Yeah. So it's compulsory to use latex.
Oh yes. Latex. Okay, later I will mention again.
Okay.
Yeah, latex.
Really, this attendance or not?
Yes, I will pass it down later.
Okay.
Yeah.
Thank you.
Right.
So when I tried it myself, I was thinking to use like a derivative. So
Derivative?
yeah, because this is discrete, right? So I don't think I can do this straight away. So
Unless you
throw
can.
it to the real function, right?
I mean, okay.
Yeah.
So I mean, yeah. I mean,
Like
yeah. I mean, it is similar to this theorem here. So if you want to say that it's increasing as a real function, then you need to prove that if it is increasing as a real function, then it's also increasing as a sequence. Yeah, you need to prove this result so that you can use.
Then I can just use this.
You need to
I need to prove that first.
yeah, you need to prove that first.
There's a blank there.
Yes.
For this question, right? I need to prove this using induction. Right?
Seems like it because you define your formula as induction.
Is there any other way to prove it?
I don't think so because you cannot use
Yeah.
n to directly see what's the term.
And I don't think I can turn this into a non-recursive function. Express it into non-recursive. Like the Fibonacci to golden ratio.
Oh, I'm not sure about this, but yeah. So one direct way is use direct induction. Yeah, I'm not sure. I haven't try out. Maybe you can, but I don't know. But yeah. But one obvious way is use induction. Okay, maybe I'll mention it later.
So for the assignment, when is the due date?
I put on the course information already.
Oh, okay.
So I think it's week 4 and first for the first week. Yeah.
Yep.
Okay. Are you here in the first lecture or not? Are you here in the first lecture?
Yeah, yeah.
You are here?
Yeah.
Oh, okay. Okay. Just asking.
I think like just now you review the bounded. I think the n no need to be natural numbers.
Wait.
Just now you review the
I'll review the bounded. Oh yeah. You mean the m? Yeah, I mean I can change it to n. I also can put it to r. But to explain this example here, maybe put r easier because my a n live in
Yes.
r. But if I put n, also never mind because I can just pick a natural number that greater than a real number.
Oh,
Yeah.
Thank you.
Yeah. I mean, yeah. Maybe sometimes you try to be fancy, or sometimes maybe in some cases you want that limit to be natural. Yeah, depend on what world or what place you live in. Some definition is useful than the other. But yeah, but I think they should be equivalent. Yeah, they should be equivalent. So if you can bound it, so if I make two definition, if I can bound by a natural, I also can bound by a real. If I can bound by a real, I also can bound by a natural number. So they are equivalent. If and only if. You can get it?
Yes. Okay.
Yeah.
Thank you.
Yeah. Yeah.
Matter whether it is R or N.
You can prove it. Make two definitions and prove it they are the same. If it can be bound by n, that means you also can bound by r because n is r. But if you can bound by r, how is it possible to bound by n? You just hit an n that is greater than the.
Oh, yes.
Yeah. So it's equivalent. If I will pass it down. Okay. Okay, I'll put down the list beside it. And okay. And then this project, right? I forgot to mention, but I mentioned in the course information. It is in latex form. You don't need to ask me about how spacing it is. So I mean, it should be reasonable, okay? You don't like, I mean, don't try and think of weird stuff to like break the rules. Like, I mean, if you make the spacing big, I also 1.5 pages. It's not, things doesn't work like that, okay? You need to express your idea well enough, okay? 1.5, why do I put 1.5? You need to have enough content, okay? If you put spacing big, for what? There's no content in your, I won't give you marks, sorry. You get what I mean? Don't try to like break the rules or what. I mean, you just need to do it properly, explain the theory well. I need a length of 1.5 pages. That's all. Okay. As a normal pages. Okay. So don't try to write too much. But still you have to come and discuss with me. Okay, so that you know what I expect, I know what you are trying to do. Okay, because this project is kind of quite free. Okay, yeah, you can prove your result or you can write something is proven. Okay, and plagiarism. So plagiarism is very important in the university. So don't try and copy paste something from some other places. Okay, use your own word. Okay, after you understand, rephrase it. Use your own word. Use your own notation. Introduce your own notation, and then write it. Okay. Make sense? Does it make sense? Okay. Okay. Yeah. Okay. just now, your classmate point out a good point here. So this homework question here, right? Define using recursive way. Okay. I'm not sure there's a general N formula for this sequence or not, but at first sight, maybe you should use mathematical induction. Okay. See that A1. Okay, yeah. I mean, I don't want to talk more first. So you can use mathematical induction if you need to show something is increasing, decreasing, so that you can use monotone. Monotonic sequence theorem. Yeah. Okay. So you can use induction here because you only can compare term here because you got an in terms of an plus 1. I mean an plus 1 in terms of an. Yes. Okay. Okay. But if you turn it to general n form, right, then you also need to use induction because you need to show that they are equal. So anyway, you cannot escape this, I think. Okay. So you cannot escape induction in this case. And there's another question maybe regarding about, just now I defined my bound using natural and real. So you can make these two definitions and then show that they are equivalent. Okay, for those who are interested. This kind of thinking is very important when you get into later courses. Okay. Show that two definitions are equivalent, or how we can relax the definition, or can we restrict the definition? Do they do the same thing? Yeah. When you go into later course, this become very important for you. For now, just left you as a question behind your mind. If you want to solve it, then you can solve it. If you don't want, then you should think about it because sooner or later you will meet it. Okay. Let's start. So next, we will start with series. Okay, so in sequences, we're only looking at the term by term, real number by real numbers. Okay, now we talk about series. We want to add a chunk of sequences together, but the way we adding the terms is following a formula or a pattern. Okay, so what do I mean by that? So an infinite series. So let's define it. So I have a definition. So note that we also deal with infinite series here. We don't deal with finite series. What is finite series? Okay, let me introduce infinite first. Then let's talk about what's finite series. So the infinite series is the form of A1, A2, A3 plus A4 to infinity. So you can think of sequences, but I'm trying to add all of them together. Okay. Add all of them together, and then I call it an infinite series. So which is denoted by sum from 1 to infinity, an, or if the index set is clear, we just throw out the index notation and put sum in infinite sum. Okay. So finite sum is easy because we can just add up together and get a number. But infinite sum is really something interesting that we can look at. Okay. So for example, examples of infinite series. Okay. So this is the infinite series. So let's look at this infinite series here. 1/2 plus 1/4 plus 1/8 plus 1/16. Do you think this diverges or converges to some number? Wow, so fast. Why? Oh, it's a geometry series. Okay. You guys learned geometry series before? Oh, okay. It's okay, good. So converges to what number, do you know? So you use the formula, is it? Okay. Let me recall the formula. So S infinity is A over 1 minus R, is it? Let me see. Yeah, okay. So it's a half over 1 minus half, which is okay. Okay, I think this one is from high school, right? Okay. Another way to think about this series is you can put into geometry as well. Okay, so you start from 0. Okay, and then maybe we have a 1 here. Okay, you first add a half. Okay, and then you add 1/4, half of a half. Okay, so you go half of a half, and then you add half of 1/4 again, and then you keep doing it, and then you keep doing it, keep doing it, keep doing it. So you can see that this like approaching the interval 0 to 1. Okay. So that's why this is called geometric series. You can draw it as a geometry object. Okay. All right, so this is just example. It's not too rigorous. Next. So to study this infinite series, right, it is actually useful to study finite sum. Okay, so let's define this. So definition. Also, although the finite sum itself is not very interesting, but finite sum of an infinite series is helpful. So the n partial sum. So we define the n partial sum of an infinite series. So this means this partial, whenever we talk about partial sum, right, it gets attached to a specific infinite series. Okay, so let's denote it as Sn. Okay, because it's labeled by n. It's just given by summing a1 up to an. In particular, what is a1? S1. What is x1? A1. Okay. So remark. In particular, x1 is just a1. Okay, then x2 is a1 plus a2 now, and then s3 is a1, a2 plus a3. Okay. Okay, so far okay. So far so good. Okay, so give an example. Since you guys are familiar with geometry series, so let's show that. Okay, give you exercise. Now show that. Let's do it as a tutorial question. Show that the n partial sum of a geometric series. Okay, how you express this partial sum? So Sn is equal to the sum of a times r to the power n minus 1, n start from 1 to infinity, or if you don't like this, sorry, this sum to n, or too many n, so I need to change my index. So this indexing is also very important in later course because you try to avoid clashing of notation here. So let's label our power as m. So summing m from n. So this is the, okay, so to be precise, this is indexing variable. This is a fixed n. Okay, so you should fix your n, and then m is running from 1 to n. Does it make sense? Very confused? I see some of you confused. So, okay, let me write down this first, and then I will tell you how to differentiate these things. So this is just equals to a plus ar plus ar squared plus dot 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 up to ar and minus 1. Is it? Yeah, minus 1. Right. Okay. So what do I mean by running n and fixed n? So fixed n meaning if I fix, for example, another example. So if I fix n equals to 3, this S3 here should stop at m from 1 to 3. Okay, which means you sum to AR squared. Okay, makes sense? So when you look at these mathematical terms, right, you need to differentiate which number is running, which number is fixed. Very important. Okay, otherwise you will confuse yourself. Okay, so can you figure out what is the partial sum? Can you give a formula for the partial sum? I will finish this sentence, sorry. So I give you target to show is actually A times 1 minus Rn over 1 minus R. Okay. So this, so yeah, so this is actually equal. So maybe I give you 3 minutes. Yeah, there's some tricky way to show it. For this kind of question, right? Okay, show that something. So this means this you can start from what is given and then try to see why it's true. Also, don't start from anywhere. So max is like that one. You have a starting point, you start from a starting point. Okay. There's a starting point I gave you already. Show that this is equal to this. So start from here. Start from there. See if you can see why this is true or not. Any idea? Long division. How to do long division? Long division? You mean, what do you mean by division? A minus ARN. Oh, okay. Oh, okay. Wait. I get what you're saying. So you say A minus ARN, and then you do long division on 1 minus half. Is it? I think that works as well. Yeah, that works as well. Long division. That works as well. Long division. Does it work? Yeah, I think it works. Yeah, you can do long division. Okay. Another way to show this long division cleanly is you can look at you can really rearrange this. So before that, maybe we do some talk first, some draft. So maybe we can rearrange this guy. Okay? And then see why left hand side is equal to right hand side. Okay? So what is 1 times Sn? So it's the whole thing, right? It's the whole partial sum. And then what is minus 1 Sn? Minus R Sn. Okay, so you multiply everything by minus R. Okay, so what do you notice here? Similar terms appear. Okay, and then they can cancel out if you move it here. Okay, so you can see that these terms actually cancel. This term similarly, you will have another R, right, minus AR and minus 1. Okay, so what you left is the first term and the last term. from the partial sum, okay, which is A minus ARN. So what do I get? Oh, I get that 1 minus R Sn equals to A plus all the way to minus R. So, okay. So this implies that Sn is equal to A minus ARN over 1 minus R. Okay. In other words, this is as what? What's your name? 主谦 or 子谦? 子谦. Okay, sorry. My need some time to learn all your names. Okay, 子谦. Okay. Yeah. So maybe this is a clean way to do long division. Yeah. Anyway. Okay. So one more thing I want to point out. I'm not sure I've used this notation before. Column and equal. Do you see me using this before? Yeah. Not yet. Not yet. Okay, so sometimes I put this column equal or equal. Okay, so these two have difference. If I put column equal, that's mean definition. Okay, by definition. So I define this as such. So this is by definition. But the equal signs here, there's some word to show. Okay. You start with right hand side, you start with something definition, and then left hand side is another thing. So you need to show that both sides equal. Okay, so this is the subtlety when I use column equal or equal. Okay. 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 So what time is it? Okay. Okay, maybe I bring out these notes. Okay, let's look at this notes here. Okay, so having talking about series and partial sum, so what are we going to do with it? So let's take a series, okay, and then we write down the partial sum, S1, S2, Sn, so on. If you have seen before, if it is a geometric series, actually we have formula for Sn. So each S you want to find S100, I also can find for you. Okay, I don't need to add all the sum, but I just put into the formula. So if Xn is convergent, okay, so if the partial sum is convergent, partial sum is a finite sum, right? Finite sum to a finite number, right? So you look at this number as a sequence. Okay, so we go back to previous subtopic sequences. If it converges, okay, that means the limit of this sequence converge to an x as a real number, then the infinite series is called convergent. Okay, and we write the infinite sum equals to that limit. Okay, so you see, so we are finding condition on partial sum and deduce something on the infinite series, right? Okay, so don't confuse here. So for infinite series, how to get a sequence? You consider what? What do you consider? Huh? I just introduced two pieces of definition just now. So from an infinite sums, what sequence you can get? Just partial sum, right? Sn. Okay. So partial sum form a sequence because every partial sum is a finite sum. Right? Make sense? Okay. So you have a sequence of number. So if this sequence of number converges, that means our infinite series equal to that limit by this definition. Okay. Maybe we will look at an example and then we will see what's this talking about. Okay, then this x is called the sum of the series. Makes sense, right? You sum together, you get that number. So sum of the series. If the sequence of the partial sum diverges, then the series, we also say that the series diverges. Okay? And a divergent series has no sum. That makes sense. A divergent series diverge, right? So no sum. If it has a sum, then it converges by definition. Okay, don't worry. Let's look at the example first. Let's see. Is this example too heavy? Let me think. How about we show the original example? I'm not sure how it works or not, but I hope it works. So let's look at the example of sum from, okay, just look at the first infinite series. So we have this running example here. Okay, we sum from half, fourth plus 8 plus 16. Okay, I'm doing experiment. I haven't prepared this. So let us try it out. So we look at this infinite series, right? Okay, let's see if this converges or not. So if you write as a compact form, what is this? N equals to 1 to infinity, which is, what's your terms here? 1 over 2 to the power of n. Make sense? So far, so good? So good. Okay, so just now we have a construction. From here, we can get the partial sum. Okay, so x1 is what? 1 over 2. Okay, we already said s1 equals to a1. x1, s2 is equal to half plus 1/4, which is equal to 3 over 4. S3 is equals to 7 over 2. Okay. 4, 8, 6, 7. Okay, 7 over 8. Okay, so you can keep going. So from here, you make up a sequence. Right? So if this sequence converges to x, then we will say that the infinite sum is equal to this x. Right? Okay. So okay, let's be practical. So we use what we learned. So Sn, what is Sn? Just now we computed, right? What's the formula? Still remember? A times 1 over r minus a to the power n minus r. Okay, so what is a in this case? Half. What is r? 1 over 2. 1 over 2. So what do you get? What do you get? 1 minus 1, 2. Okay, good. So this is a perfectly well sequence. Okay, we go back to previous section already. Does this sequence converge? Why? Okay. Over to n. Converge to 0. Okay, we haven't shown it, but it converges to 0. Okay, so limit n to infinity Sn, which is actually suppose we know that, okay, 1 converges obviously. Suppose we know that 1 over 2n converges to 0, then we can use the property of the limit again to break up the sum, and then we get, what do we get? What do we get? We get 1. Okay, 1 minus 0. Okay, so this is our S. Okay, so this is defined to be our S. So this means that the infinite sum is actually equal to 1. Okay, make sense? Make sense? Okay. Okay, cool. So I show it to you that this this infinite sum is equal to 1 using the sequence definition, I mean series, convergent series definition. Also show you geometrically why it is equal to 1. And yeah. Okay. Let me see, what should we do next? Okay. Maybe try this one. Okay, so I let you spend about also 3 minutes think about this question here. So how to show a geometric series converges? Okay, but there's a condition. The R have to be in between -1 and 1, if and only if. So it go both directions. So if it converges, then R must be in between -1 and 1. If R is in between -1 and 1, then it converges. This geometric series converges. I think of it. So you can think about to show infinite series converges, what's the definition? What sum you need to look at? Partial sum. Okay. So try to look at the partial sum. What happened to the partial sum? Does it converge? Okay. We already found the n partial sum formula, right? Just now for general A and R. So use that formula. See if you can show something useful. So let me write down what I just said. So look at partial sum. In the partial sum. Okay, did anyone successfully see something or not? Okay, if you look at this partial sum here, okay, there are a few sequence going on, right? There's a 1 minus R, there's a A, there's a 1 minus Rn, right? Okay. Is A converging? Yes, right, it's just a constant sequence. 1 minus R is also a constant sequence. Okay, so we can bring our limit all the way inside here. Okay, but inside here you still got two sequence here. Okay, one is converging, Rn converge or not? Not sure. Yes, not sure. Okay, let me write it down, then I will review more. Yes, right, not sure. Depend on R, right? Depend on R. How does it depend on R? Anyone have remember something that we did? Last time we determined when is R to the n converging, right? Okay, so anyone remember the range or not? Anyone can remember the range? -1 to 1, and then converge to what? Converge to what? 0. Okay. So only if and only if only if I think if only 0. Okay. So you see this condition of on R appears when you need to determine whether this conversion. Okay. So from this step we have the condition popping up, and this term is actually 0, so we get A over 1 minus R. Okay, so keep the condition. Okay. Less than or equal to 1, right? Or equal to, I mean, actually it also converge at I equals to 1, but converge to where? When I equals to 1? 1. So if this, because we don't want 1 already, otherwise this thing will soup to infinity. Okay. So we already throw 1 away. So we restrict ourselves to -1 to 1. Okay, make sense? Okay. Okay. Is that all? I think that's all. So you see, so we found the S infinity formula here. So this is the F infinity, which we usually call the geometry series, right? S infinity. Is this what you call when you first see this in the high school, secondary school? I mean, this is equals to. Okay, maybe you write it as a compact form. So try to get used to this compact form. It will help a lot when you need to write something compactly. Okay. Okay, so far okay. Yeah. All right. So maybe I also left this one as an exercise. Okay. So see if you can look at left as exercise. So homework. So how many ways you can show something is convergent or not? For now, what have you learned? What have you learned? What have you learned? Always think about what have you learned. So there are actually 2 ways to show something is converging now. Okay. One is straightly from the definition. Second, we have proved geometric series. So if you can write your series as this kind of term and make sure that the R is in between the right range, then it is also converging. Okay, so now you have at least 2 ways to prove something is convergent. Okay, so don't try to think this is nothing. Every examples we show in the class is very important. Okay, it will be very useful for the next question, for future question. Okay. Yeah, so there are 2 ways to do. Either you can show from definition or use geometric series criteria. Okay, make sense? Making sense? Okay. All right. So I want to do one more fun exercise. So, or maybe we skip this. Or okay, maybe let's skip this then. Maybe we do it next time. Okay. Let's look at the next one. This one application example, I think I also skip this. You can do it. I will post the solution afterward, and then you can compare the solution. Okay, maybe we do this. Let's do this. Show that the series is convergent by expressing xn as a telescopic sum and finite sum. So I haven't introduced what is a telescopic mean. So telescopic is like how to say? Do you know what a telescope is? Okay, so you get yeah. Okay, so yeah, okay. Maybe I just show you and then you will make your decision. What is it? So okay, let's look at this example here. 1/4n squared minus 1. Okay, so 4n squared minus 1 is the difference between two perfect square. So you can write it in terms of two factors, which is 2n minus 1 and 2n plus 1. Okay, you can split this. In fact, you can split this into two what do you call this? Two fraction. Two fraction, okay. Any name for this method? I forgot. Oh, partial fraction, good, very good. I forgot what's the name for this. I think I learned it during the when I studying matriculation partial fraction. It's good. Okay, good. So can you find A and B such that this is true? You can do it by substitution into this. Rearrange the equation where you multiply the denominator across. Okay. From here, what can you do? You can substitute some numbers for n, right? To find some condition between A and B. Or in this case, maybe you can use inspection, where just guess what is A and B. If it satisfies this equation, then it's good. Okay. So to save time, let's do inspection. You can do substitution. Okay, you can do substitute some n and then find some condition on A and B. I mean, of course, the n you pick need to be clever, right? Okay, so you can pick the root of the polynomial so that you get rid one of them and then you have only condition on A. Right? So I just mentioned here, but I don't want to do it. So pick n as the root of the factor 2 is the calculation. Otherwise, you need to do the system of linear equation and then, yeah, right, yeah, okay. Otherwise, by inspection, I straight away get this answer: A equals to half and B equals to minus half. Okay. So we will demonstrate what we call by a telescopic sum here. So in this case, we'll write this fraction is equals to 1/2 times 2n minus 1 minus 1/2 times 2n minus 1. Okay. All right. So you notice that. What do you notice? What do you notice here? I can bring out this half first, and then we'll see soon. Okay. So what is this really doing? Okay. What is this really doing? Okay. Maybe we write the partial sum up will be clearer. So let's write out what is S1. Okay, so what's S1? So S1 is summing 1/4 times. Okay, let's write out the partial sum formula first. So what we do, okay, you see there's a notation clash again. Okay, so we just change the notation. So that means we truncate when we look at the partial sum, we truncate the infinite series. Okay, we just truncate it. I will up to n. Okay, so what is 1? x1 is 1 over 4 times 1 minus 1. Okay, by the formula, we also know that, what do we know? We know that this is equal to half of 1 plus 2 times 1 minus 1 minus 2 times 1, sorry, 1, which is half times 1 minus 1 over 3. Okay, nothing interesting yet. Okay, never mind. So let's keep going on. So what is x2? What is x2? So x2 is 1 over 4 times 1 minus 1 plus 1 over 4 times 2 over 2 minus 1. Getting more complicated. Okay, but on the other hand, what do we have? 1 over 2 times 1 minus 1 minus 1 over 2 times 1 plus 1 plus, oh, this is from the first term, plus 1 over 2 times 2 minus 1 minus 1 over 2 times 2 plus 1. Does it make sense? Making sense? So we get 1 over 2 over 1 minus 1 over 3 plus 1 over 3 minus 1 over 5. Okay. So you can see that there's some cancellation going on now. Okay. So similarly, if you write longer, so you could imagine when you get longer, when get 1 over 2 times 1 minus 3 over 1 over 3 plus 1 over 3 minus 1 over 5 plus 1 over 5 minus 1 over 7. You can verify it and then you keep going on. So you can see that when you get n large, the middle term actually cancel. Okay, what you left with is the first term and the last term. Okay, so what does this mean? So what does this mean? So if we put this all together and then we compute for Sn, and let me write down. So n equals 2. Okay, maybe I put I now. So for I squared minus 1 equals to sum of I equals to 1 and half of this formula here. Okay, 2i 1. Okay, and then you can try to write a few terms up to see the pattern, and really you'll see that the middle term get cancelled. What you left with is just the first and the last term. So what's the last term? It's actually 2n plus 1. Okay, so this means this guy will cancel, then those guys will cancel. Then what you left is 1 minus 1 over 2 to the n plus 1. Okay, so this is perfectly another good sequence. Okay, so check this sequence converge or not. Does it converge? Yes, okay, because half is a constant sequence, 1 constant sequence, and then this guy go to infinity. Or this guy, this whole guy converge to 0. Okay, so limit. So whatever I said just now, you should write down in your assignment. For now, I just write out the whole step is equal to. Okay, so things, the partial sum converge to half. This is our x. Then the infinite series is equal to x. So by definition, the infinite series is convergent, and the limit is half, and the sum is half. If it doesn't converge, then there's no point to talk about sum. Okay, you cannot, yeah, no point to talk about sum. Yeah, it diverges, then no point to talk about sum. Okay? So far, okay? All right, okay. To be clear. Okay, next, before we end, let's see how much we can do. So, test for divergence, okay? So, now this is a test for divergence of series, okay? This is a series for series. So, if the series sum to infinity, the infinite sum converges, then the individual term here, this is an, not Sn. This is not partial sum. This is individual term an. The limit of the an go to 0. Okay, so you might say, hey, this one talk about convergence. You say you want to test for divergence, right? So remember the logic is if P then Q, right? Okay, so this is equivalent to X contra positive. So which means is equivalent to if not Q, then not P. Okay, so very important. Whenever I talk about a theorem, right, you should immediately think about the contrapositive because it can show something else. So in this case here, if you can show that your limit of your individual term is not 0, then the infinite sum will diverge. Okay, so are we going to show this? Okay, maybe actually, right, to prove this sentence here, actually the contrapositive is easier to prove, I guess. Is it true? Maybe it's not true. Okay, never mind. Yeah, but we won't prove this, I guess. Okay, but if you are interested, you can try and prove it. I mean, yeah. But for a project title, I think this one is too easy. If you want, maybe you can collect a few easy results also can. Yeah. So you got a few easy results that you prove you want to do as a project also can. But cannot just be one easy topic. What time is it? 12:50. Maybe we stop here. Okay. We stop here for next time. And then all right. So think about the project, what you can do, and then try and talk to me more because this is also the first time we do this. So we try to make this both good for both of us. Okay. Okay, thank you.